Hello, apes, and welcome to our fifth screencast in the Chapter 2 series, and that is Earth's physical systems, matter, energy, and geology. And we have been talking about macromolecules, and we have been looking at, the polymerization of those molecules and what makes up those molecules, just a refresher of what you had in biology. And we now want to talk about the carbohydrates. And remember, carbohydrates consist of carbon, hydrogen, and oxygen, and that was in a 1 to 2 to 1 ratio. So like that C6H12, C6H12O6 of glucose, we can definitely see 1 to 2 to 1 ratio here, and that this 2 to 1 ratio is water. So it's carbon and water that comes together. So our carbohydrates are going to be our sugars, and we have simple sugars which we call monosaccharides, and they are carbohydrates of anywhere from 3 to 7 carbons in their backbone. So glucose is the one example that you're most familiar with. Fructose is another example of that. Galactose would be another example. We have complex carbohydrates that are polysaccharides. So complex carbohydrates are going to be your polysaccharides like your starch and your cellulose that you're familiar with. Starch, again, it's an energy source or energy storage in plants. So we eat the plants to get that energy from the starch. You might not have heard of this before. Chitin, and this is the substance that forms the shells of insects and crustaceans like shrimp. That's also made up of starch. And cellulose, which you probably have heard if you had me, and that is in the cell walls of plants. So these are carbohydrates, the significance of carbohydrates. We did leave out disaccharides. Disaccharides would be like sucrose, the table sugar, and maltose that you might be familiar with in some of your foods. So those are our macromolecules. Now we've got to go and we've got to refresh ourselves about energy. And again, these are things that you've heard before one time or other in biology or chemistry. And energy, just by definition, is the capacity to change the position, physical composition, or temperature of matter. And it can involve one of three ways. Either a physical process, a chemical process, or a biological process in the way that energy can be used. So when we think of chemical energy, we think of it in terms of potential energy, and that's the energy that is stored energy. I want you to remember that term endergonic. And endergonic is where you have energy that is stored within the bonds of a compound. So potential energy, again, anything that is stored, energy of position, it's not being released yet. So nuclear energy, mechanical energy. You could be sitting on a bicycle and not going anywhere, and that's potential energy that you have. Kinetic energy, then, is the energy of motion, and I want you to think of exergonic, where it's releasing energy. That energy is being released, so it's coming out of. So we're thinking of thermal energy, when something gives off heat. Light, you got the lights on overhead, or the light that's coming from your screen as you're watching this. Sound, electrical, subatomic particles. Okay, that's kinetic energy. That's the energy that's in motion. We're on that bicycle, we're riding that bicycle down the hill, we're pedaling, we're putting that energy into motion. Chemical energy is a form of potential energy, and that chemical energy is what's held between the bonds of the atoms that's going to hold a compound together. So chemical energy, when the bonds are being held together, that is an endergonic type of energy. When we're breaking the bonds, we're using that glucose in the process of cellular respiration. That's an exergonic reaction that's taking place. All right, so again, if you're unsure of any of these, then please make sure that you refresh yourself on those terms. So here's potential energy. We're going to have starch in a lot of our foods. That's what's pictured here. So glucose. We take oxygen and put that together. This is the formula for cellular respiration. And then when that all breaks down, it provides us with energy, ATP energy, which is not depicted in this equation, and some energy is given off as heat. That ATP energy that we have, that adenosine triphosphate, is going to be used to give us the kinetic energy, that energy of motion, so that we can move, we can do our activities. Okay, energy is always conserved, but it changes in quality. So that's something that we need to know. We didn't discuss this in biology, but you might have had it a little bit in chemistry if you had honors or AP Chem. And we're going to talk about the first law of thermodynamics, and that says that energy can change forms but cannot be created or destroyed. So that's kind of like the law of conservation of matter, or the law of conservation of mass. It can change forms, but it cannot be created or destroyed. So if we have the energy that comes in the form of heat, it cools down into something else. Okay? The second law of thermodynamics is that energy changes from a more ordered to a less ordered state. And we often refer to this as entropy, which is an increasing state of disorder. So if we put energy into something, like, we're heating up water, we're boiling water, it's going into that water and it's changing so that those water molecules are bouncing off of each other and creating friction, and it's just going everywhere. You can have it in your container, but you really can't contain the steam coming off of that. So inputting energy from outside the systems increases the order, and that's what we need to think about. So here we go. We've got potential energy that's stored in these logs. And when we light that activation energy that lights it, we wind up getting a fire that gives off light and heat and water and carbon dioxide. And in order to get that, we get that entropy where at the end it's ash. It's ash, it's smoke that is left over. So that's a really great example of those laws in action. So an energy source's nature determines how easily energy can be harnessed. So that's when we start thinking about what are the things that we use for energy, and one of the first things that we really use are fossil fuels, and that they provide for us, as it says here, a concentrated energy. It's an energy source that we know, gasoline, that if we just spark it, it can fuel our cars, and it's concentrated. We can use a certain amount. Where when we think in terms of sunlight's not so concentrated. It's spread out. It's being collected temperature-wise in the oceans. It's being collected within our plants to make glucose. It's warming up the surface of the earth, and it's really a little bit more difficult to harness because you've got to create things to trap that energy. So when we think about the conversion of energy, we want to think about it in the terms of efficiency. So energy conversion efficiency is the ratio of useful energy output to the amount of needing to be input to get that. So let's think about that with our fuels. 16% of the energy released from gasoline is used to power an automobile. 16% of that energy in gas is used to move your cars. So what happens to the rest of it? It's lost. You're not using it. It's lost as heat. Your engine gets really hot. It doesn't get used for anything. Where only 5% of an incandescent light bulb's energy is converted to light. So that's a regular light bulb, and only 5% of that is converted to light. But if we have the new mercury lamps, the lights, we're talking about maybe 40, 50, 60% depending on the wattage that you're dealing with there. So that kind of conserves that energy. The sun is going to release radiation, and that radiation is in the form of the electromagnetic spectrum. So Roy G. Biv, the rainbow, and then the lights that you cannot see. And that solar energy is going to drive the weather and the climate, and it's going to power the plant growth. So we've got a lot of energy in that solar light. We use microwaves. We've been able to harness microwaves that can actually cause elements and atoms to move quicker, cause more friction, and heat things up faster. So that's a form of energy that we have there. We've got solar panels that can collect that energy of sunlight and store that energy in cells. Okay, so that's part of the power. It regulates the climate, the way that it heats the Earth's surface, or the way that it reflects off of the snow. All of these are essential in regulating the climate. And then we know that plants rely on it to produce glucose. They rely on it for cell growth. So let's talk about the organisms that use sunlight. And they are autotrophs, or primary producers. So they're the self-feeders. They're the ones who can take that energy from sunlight and convert it into glucose. They can produce their own food. So these are going to be organisms like green plants, algae, cyanobacteria. Those are our autotrophs. And they use the process of photosynthesis, where they're able to convert that sun's energy along with water and carbon dioxide, and they're able to make a form of energy in a carbohydrate, in a sugar. It's a concentrated chemical energy. Now that chemical energy, remember, is in the bonds. So it's stored in those bonds, and because carbohydrates can break down so quickly in the presence of water, it's a quick release of energy. Here's that electromagnetic spectrum that we were talking about. In this particular area, this is the light that is visible, that we can see. So that's our rainbow. And then on either side, this is the energy that we cannot see. And as you notice, the wavelengths change. And these wavelengths are the source of energy, because the distance that it takes from each wave is how quick that energy is. So see, these are really far apart. So this is a lower amount of energy, where these are really close together, and that's a higher amount of energy that you're going to get. So think of being at the beach, and it's a lazy, warm, sunny day, no wind, and the waves are just gently rolling in, versus if there's a storm out in the ocean and the waves are just slamming one right after the other, and how more aggressive and more energy is coming with those waves. It's the same idea with the electromagnetic spectrum. Okay, we're running out of time with this screencast, and we'll start with this one in the next one.